Okay, let's get started. I think we left off somewhere around kernel threads. So yeah, anyway. Kernel threads. It is often useful for the kernel to perform some operations in the background. The kernel accomplishes this via kernel threads. These are standard processes that exist solely in kernel space. So they are tasks that only run in kernel space, special, they don't break out user. They just live inside kernel, and the kernel runs them normally. The significant difference between kernel threads and normal processes is that kernel threads do not have an address space, so they don't get their own virtual address space like user processes do. User space tasks do. The pointer, which is part of the task struct, I assume, uh, which points to the appropriate address space, is null. So if we were to go back to, let's say, task, was it task dot c? Uh, oh, that's a lot of task dot c. Let's do the regular task dot c. We should have, I don't even remember, was it kernel slash task.c or Linux task.h task. Uh, let's ask AI. Uh, see, where is task struct defined in the Linux 2.6 kernel? Okay, so task struct is a fundamental data structure, blah blah blah, according to Linux kernel source code. It's in Sketch H. Okay, not task. Sketch H. Kernel include Linux Sketch H. Okay, so if I did that, I could do kernel Linux Sketch H. So maybe like that. I could do that. Or just Sketch H. Include. Wait, kernel include Linux. Let's try that again. Kernel include Sketch Linux. Include Linux Sketch H. Bizarre. Should be, oh, right there. Okay. Sure. Okay. And then where was it say? It's defined as struct task structs. Okay. It has all these other fields. I want to see the code though. I keep forgetting where that is, so let's just get used to it. So it should be in here. These are all the clone flags as we remember from last time. It's good for us to know. The problem with this is that all these macros make it really hard to read the code. Um, but I could search for it. I mean, yeah, struct task struct is here. But that doesn't look like that's the full definition. Uh, let's do this. Task struct like this. Okay, cool. We do have it right here. So really far into the file, line 1170, we had the um was it declaration up at the top, but it's not defined until much later. So there should be an pointer somewhere here. So if we take a look at, I'm just gonna keep going down. So tasks, struct right here. Oh gosh. Okay, right here. So struct. We take a look at Maybe let's see. Can we easily find struct, or do we need our LLM again? How would we do this? Do we get anything if we were to? Oh, that's interesting. We did get something, but okay. Struct struct. Okay. So right here, if we were to go to this file, include Linux types, we will have basically this struct here that defines, I guess, the address space stuff. Yeah, lots of stuff. Not sure what that really means yet, but good to know we can at least find some of these things. So, yeah. So they will have an pointer that will point to null for kernel threads. So they operate only in kernel space and do not context switch into user space. Okay. Kernel threads, however, are schedulable and preemptible, the same as normal processes. So they are scheduled just like user space processes too, they being the kernel threads. Linux delegates several tasks to kernel threads, most notably the flush tasks and the ksoft irqd task. You can see the kernel threads on your Linux system by running the command ps-ef. Okay, and there are a lot of them. Really. Let's see, ps-ef. Okay, so where would I see them? Is it because is it all the K ones? Uh, okay, let's do this. PSEF, ksoft, irqd. Do we have one? No. Oops, grep. Grep. Oh, we do have them right here. Okay. How about flush? Oh, okay. So these are common ones. Okay, cool. So we do see them. We would do ps-ef grep for whatever kernel thing that you're looking for. I'm guessing that the kernel stuff is like square bracket, I would assume. So, okay. Kernel threads are only, how do I get rid of this? Kernel threads are created on system boot by other kernel threads. Indeed, a kernel thread can be created only by another kernel thread. Okay, so kernel threads are created on system boot by other kernel threads. And indeed, a kernel thread can be created only by another kernel thread. So you can only create a kernel thread only through another kernel thread. The kernel handles this automatically by forking all new kernel threads off the kthread-d kernel process. The interface declared in Linux kthread-h for spawning a new kernel thread from an existing one is this one. Okay, so we were to look at kthread d, kthread, is it kthread-d? Kthread, or kthread.h. Kthread.h. So kthread.h. Okay, we found that. And then here, kthread create is the function that will return back a task struct specifically associated with the kernel thread. Okay, I think this is just this one is just a declaration. So if we do kthread c, maybe that will have it. So kthread.c, guessing this one, and then kthread create. Kthread create right here. So this one is a definition. So here, create a kthread. So kthread fn is the function to run until signal pending current. Data pointer for a thread function, so probably a parameter to pass in. Yes, right here. And then the name format, print style name for the thread. Okay, cool. So this helper function creates and names a kernel thread. The thread will be stopped. So when it gets created, it'll be stopped. Use wake up process to start it. Sure. So kernel thread might be created, stopped by default. When woken, the thread will run thread function. So that's our callback function with data, the data that we passed in, as its argument. thread function can either call do exit directly if it is a standalone thread for which no one will call kthread stop, or return when kthread should stop is true. This means that kthread stop has been called. The return value should be 0 or a negative error number. It will be passed to kthread stop. Okay. So looks like it uses a spin lock to create the kernel thread. Adding it to the list, I guess. Okay. Well, exactly. Doesn't look too bad actually. It looks pretty small. So it uses probably these helpers here. So create thread info. Sure. Anyway, the new task is created via the clone system call by the kthread kernel process. The process will run the thread fn function, which is past the data argument. So going back here, notice how we had the create thread fn and then the create.data. I wonder if somewhere here create result. Okay, so maybe that will actually contain the result of running the thread fn and the data. Init completion maybe is what is actually run. So let's see, go here, init completion, halt and declare. Okay, let's do init completion. Huh, interesting. Sure. I'm guessing it just calls the. No, that's not right. Wait for completion. Yeah, so where would it call? Oh, that's right. Because it's not really running until yeah, it's sleeping first. Okay. Okay. Let's go back to what it was saying again. The new task is created via this clone system called by the kthread kernel process. The new process will run the thread fn function, which is past the data argument. The process will be named format, named fnt, which takes up printf style formatting arguments in the variable argument list. The process is created in an unrunnable state. It will not start running until explicitly woken up via wake up process. A process can be created and made runnable with a single function kthread run. Oh, okay, so that is a separate process with kthread run. Okay, so if we look at this and search for kthread underscore run, where would that be? Let's look at this. Okay, where is kthread run defined in the Linux 2.6 kernel source? You know, I think this thing times out once in a while, which probably says so it never does that. So, but I think that's for another time. Not super critical. We can just wait for it to load. It's not too bad. Another great question. All right. Kthread runs a function that creates and starts a new kernel thread, also known as a kthread. This function is used to create threads within the specific, well, within the kernel context. Okay, we can find it in exit.c, kernel/exit.c. Contains several functions related to process and thread management, including kthread run. So this is where we want to go. Okay. Sure. Let's do it. Okay. We're at exit.c. Okay. Exit.c. I hope there's not like a ton of them. Okay, kernel exit.c. Then we're going to look for kthread run. Kthread. What? Kernel exit.c. Kthread run. kthread run. Kthread run. What file is this? Kernel exit.c. I'm right, right? Kernel. Yeah. Oh, one of those things again. Should be right. Run. How about kthread? We parent to kthread. I guess. Let's look for kthread run. Probably should have done that earlier. Trying to find all this stuff. Okay. Probably did this. This? Kthread run. Huh. Where would be our definition? Spin lock, suspend. It's not quite obvious where that's defined. I don't want to spend too much time, but I don't even know what the signature would be too. I'm just looking at the side here as I'm scrolling down, just hopes that I see some sort of thing that looks like a definition. Still don't really know how to navigate around yet. So I think part of it is just memorizing, to be honest. Okay. Oh, wow. Okay, so it is here in kthread.h all along. So define kthread run, kthread create. Okay, we were there. And then wake up process with this struct that is returned by kthread create, which we were there. Okay. Wake up process. Okay. Wake up process. Wake up process. Where is that defined in? Probably sketch. Sketch.h. Int. Oh wait, come on, I was there. Sketch.word. We saw it in sketch.h, right? Sketch.h, sketch.c. Right there. Try to wake up. Try to wake up. Okay. Try to wake up. Okay. Try to wake up a thread. Okay, so this is eventually all goes into here, which I guess wakes up the thread and starts to schedule it correctly. Okay, not gonna go too deep into it. It's distracting. Okay. Anyway, so basically, kthreads are not run right away. When they are created, they are stopped, and then we have to explicitly start them separately. Okay, with the kthread run call. So this routine implemented as a macro, I should have probably read deeper, and it's right here. Simply calls both kthread create and wake up process. Okay. When started, a kernel thread continues to exist until it calls do exit, or another part of the kernel calls kthread stop, passing in the address of the task structure created returned. Passing in the address of the task structure returned by kthread create. See, so we use this with the structure from this function call create here to stop kthreads. All right, we discussed specific kernel threads in more detail in the in later chapters. I have a feeling this is gonna be the hardest part here, just like this whole kernel thread thing. Okay. Process termination. It is sad, but eventually processes must die. When a process terminates, the kernel releases the resources owned by the process and notifies the child's parent of its demise. Generally, process destruction is self-induced. Whoa. Okay. It occurs when the process calls the exit system call. So we've used this one a lot in C programming. Either explicitly when it is ready to terminate or implicitly on return from the main subroutine of any program. That means the main function. Okay, that is the C compiler places a call to exit and after main returns. Yep, exactly what we just said. A process can also terminate involuntarily. This occurs when the process receives a signal or exception it cannot handle or ignore. Regardless of how a process terminates, the bulk of the work is handled by doExit defined in exit.c. The bulk of the work is handled by doExit defined in exit.c, which completes a number of chores. It sets the PF exiting flag in the flag's member of the task struct. Okay. It calls del timer sync to remove any kernel timers. Upon return, it is guaranteed that no timer is queued and no timer handler is running. Okay, so any related timers to the process is just done. If BSD process accounting is enabled, doExit calls the ACCT account update integrals to write out accounting information. So meta stuff, I'm guessing. It calls exit mm to release the mm struct held by this process. So like throw away all the virtual address space stuff. Is it? Let's see. If no other process is using this address space, that is, if the address space is not shared, the kernel then destroys it. Okay. Okay, I understand this. Okay, so like a process has its own virtual address space because it thinks it's the only thing in the system, and the task struct has a pointer to this address space, and a task struct is a process, right? This is the pointer, which is basically the struct that we saw earlier. That represents the virtual address space. Remember that the process itself has its own, but then in Linux, there's no distinction between a thread and a process aside from the fact that the thread will just share the same virtual address space and a couple other things. So basically, if you are terminating a process and there aren't any other tasks, right, that are using this struct, basically this will get cleaned up with exit associated with this process. And then it calls exit sem. If the process is queued waiting for an IPC semaphore, it is dequeued here. Then it calls exit files and exit fs to decrement the usage count of objects related to file descriptors and file system data respectively. If either usage counts reach 0, the object is no longer in use by any process and it is destroyed. It sets the task's exit code stored in the exit code member of the task struct to the code provided by exit or whatever kernel mechanism forced the termination. The exit code is stored here for optional retrieval by the parent. Okay. So exit code property in the task struct. So it sets it to the code that was provided by exit or whatever kernel mechanism forced the termination. Okay. And then you know how we had that whole wait PID system call by the parent process to retrieve the exit code of the child process after termination. I think this is where the whole wait PID thing actually gets like where wait PID actually kind of retrieves the exit code from that child, because when the child exits, that exit code is set on that process that's getting killed or terminated. So then the parent can pick that up. Okay. It calls exit notify to send signals to the task's parent, reparents any task's children to another thread in their thread group or the init process, and sets the task exit state stored in exit underscore state in the task struct structure to exit zombie. So the state of the process becomes a zombie process. Okay, so it doesn't like get killed right away. It becomes what we call a zombie. Okay, so do exit calls schedule to switch to a new process because the process is now not schedulable. This is the last code the task will ever execute. Do exit never returns. At this point, all objects associated with the task, assuming the task was the sole user, are free. The task is not runnable and no longer has an address space in which to return and is in the exit zombie state. The only memory it occupies is its kernel stack, the thread info structure. So thread info structure and kernel stack are synonymous here. And the task structure. Okay. Well, is it? Wait, hold on. I read that wrong. The only memory it occupies is the kernel stack, the thread info structure, and the task structure. Okay. This task exists solely to provide information to its parent. After the parent retrieves information or notifies the kernel that it is uninterested, the remaining memory held by the process is freed and returned for system use. Okay. So removing the process descriptor. After do exit completes, the process descriptor for the terminated process still exists. So even though after do exit is done for that process, it's not completely like gone from the system yet. The process, remember, had a exit zombie state set to it, so we consider this a zombie. So it says, but the process is a zombie and is unable to run, meaning that it is not schedulable. As discussed, this enables the system to obtain information about a child process after it has terminated. Cool. Consequently, the acts of cleaning up after a process and removing its process descriptor are separate. So, cleaning out the process, which is like the exit step that we just discussed, and then actually removing the process descriptor from the system are two different things. After the parent has obtained information on its terminated child or signified to the kernel that it does not care, the child's task struct is deallocated. I wonder when that happens. Anyway, the wait family of functions are implemented via a single and complicated system called wait for. Okay. The standard behavior is to suspend execution of the calling task until one of its children exits, at which time the function returns with the PID of the exited child. Okay? I'm trying to get my tablet working. It was working earlier. Okay. Additionally, a pointer is provided to the function that on return holds executable. Okay. When it is time to finally deallocate the process descriptor, release task is invoked, and it does the following. It calls the exit signal function, which calls unhashed process function, which in turn calls detach PID to remove the process from the PID hash and remove the process from the task list. Okay. The exit signal releases any remaining resources used by the now dead process and finalizes statistics and bookkeeping. Okay. If the task was the last member of the thread group and the leader is a zombie, then release task notifies the zombie's leader's parent. So, wow. Okay, so task management itself is very, very separate from just like where all the task stuff happens, I'm guessing. Ugh, this is gonna be tricky to navigate around. Release task put task struct to free the pages containing the process's kernel stack and thread info structure. The process kernel stack and thread infrastructure. You know what? I'm gonna ask the LLM, like, what's the difference between kernel stack and thread infrastructure? I'm confused. So not ask, but clarify. Okay. What's the difference between the kernel stack and thread info kernel stack and thread info struct in the Linux 2.6 source code. And you know what? Let's do this. Let's finally edit our Llama thing so that it doesn't time out often. I need to look it up. It has to always reload the model after every few minutes. Llama increase timeouts. Is it timeout? Or model, or keep alive. Increase keep alive. It's called keep alive, I think. Environment variable. Llama underscore keep alive. Let's see. Oops. Keep alive. My head says underscore, so. Okay, so keep alive would be leave it in memory to use. -1. -1. Okay. So how do we do that? How to configure a Llama server correctly to set the environment variable. Right here. Systemctl edit Llama.service, and we just add it right here. And then Llama keep alive is, I think, separate like this. And then we'll want -1. Okay, let's do it. Let's see. Sudo systemctl edit Llama.service. Okay. What do we do? Service, okay? So, service, and then we'll have environment equals Llama keep alive equals -1. I'm guessing that's all there is to it. And then this thing's still going. Okay, well, it's still going. Let's just. Okay, so our question was here. In the Linux kernel, both kernel stack and thread infrastructure structs play crucial roles in process and thread management. The kernel stack is basically a task struct. Really? Okay. The kernel stack is part of the task struct. Oh, it's part of the task struct, which represents a process or thread. It's located at the top of the stack, and its main purpose is to store data that needs to be preserved across the context switches. So literally kernel stack. So like stack memory that is going to exist across all processes. It's the same one too. So it's like thread registers, thread local storage, kernel specific flags. Okay, how about thread info? The thread info struct, on the other hand, is a separate entity located at a fixed offset from the thread's kernel stack. It contains information specific to each thread, such as thread flag, CPU affinity, timekeeping data, scheduling parameters. So per thread. The thread info struct is not stored on the process's main memory heap, but rather at a fixed offset from the kernel stack. This is because threads share their parent's address space, and they need to access some thread-specific information without allocating additional memory. Okay, so there are two different things. One is, I'm guessing, more for the kernel, and one is more for the thread. Okay. Sure. Let's also restart Llama. Bye. Oh, okay. Wait. This is good. In summary, the kernel stack is used for general purpose stack operations, while the thread info struct contains thread specific information used by the schedule and other kernel components. So when the book keeps using kernel stack and thread info in the same sentence, which I have had a hard time comprehending, they are meaning two different things. Okay, two different things. Okay, so sudo systemctl restart llama.service. Okay, llama run llama 3.1. That's the default 8 billion parameter model. Okay. Moving on. At this point, the process descriptor and all resources belonging solely to this process have been freed. Okay, so this is the real full release cleanup. I guess, zombie. If so, the dilemma of the parentless task. Okay, so what happens if you kill a task, but that task had like children? Okay, so if a parent exits before its children, some mechanism must exist to reparent any child tasks to a new process, or else parentless terminated processes would forever remain zombies. Oh, maybe this is what we were seeing when we were one time we were doing the whole exec thing, and then I think I saw like some processes that were zombies hanging. I think this is the behavior. Yeah. Okay. So, yeah. So forever remain zombies, wasting system memory. The solution is to reparent a task children on exit to either another process in the current thread group, or if that fails, init process. So reparent, move the children to a new process to be for that process to be new parent. Do exit calls exit notify, which calls forget original parent, and which in turn calls find new reaper to perform the reparenting. Okay, so here's the code to actually do the reparenting. So thread here. Let's see. Okay, so you're gonna assign the father thread to whatever this local thread variable is here. Um, Looks like it's just trying to find the appropriate thread to be the new one, I guess. Huh. Okay. This code attempts to find and return another task in the processes thread group. If another task is not in the thread group, it finds and returns in a process. Now that a suitable new parent for the children is found, each child needs to be located and reparented to Reaper, the variable named Reaper. So Reaper is assigned with the return result from find new Reaper. Okay, and then it just iterates through the list for what? Hmm. Okay. So looks like it's still doing that whole reparenting thing. Huh. Okay, so ptrace exit finish is then called to do the same reparenting, but to a list of ptrace children. Not sure what ptrace is. Tracer? Process tracer maybe? Okay. Man, this is hard. Okay. So we're gonna exit ptrace. Ptrace exit ptrace exit finish is then called to do the same reparenting, but to a list of ptrace children. So this is the function that gets run when ptrace exit finish. Okay. Oh, this is just an example of another situation where reparenting occurs. Okay. Sure. Okay. Anyway, the rationale behind having both a child list and a ptrace list is interesting. It is a new feature in the 2.6 kernel. When a task is ptrace, it is temporarily reparented to the debugging process. When the task parent exits, however, it must be reparented along with its other siblings. In previous kernels, this resulted in a loop over every process in the system looking for children. The solution is simply to keep a separate list of processes children from being ptraced, reducing the search for one children from every process to just two relatively small lists. Reducing search for one's children from every process to just two relatively small lists. Okay. With the process successfully reparented, there is no risk of stray zombie processes. The init process routinely calls wait on its children, cleaning up any zombies assigned to it. Okay, so conclusion. In this chapter, we looked at the core operating system abstraction of the process. We discussed the generalities of the process, why it is important, and the relationship between processes and threads. We then discussed how Linux stores and represents processes with the task struct and thread info, and how processes are created via fork and ultimately clone, how new executable images are loaded into address spaces via the exec family of system calls, and the hierarchy of processes, how parents glean information about their deceased children via wait family of system calls, and how processes ultimately die, forcefully or intentionally via exit. The process is a fundamental and crucial abstraction at the heart of every modern operating system and ultimately the reason we have operating systems together, which is to run programs. The next chapter discusses process scheduling, which is the delicate and interesting manner in which the kernel decides which processes to run and, and what time and in what order. Okay. I wonder if we can practice a print statement in the kernel and compile it and then try to see if we can take a look at what's inside a specific task struct. Let's try that. There was this one loop I was interested in. Uh, it was in the book it was this code will never fail or something like that. It looks something like this. It pointlessly prints the name and period of each task. Let's just try doing something like this. For each process, given this task, print k task com task pid. It's expensive to do that. Let's do it. Okay. Yeah, let's print some of the process family tree stuff. But the question is where? Huh. Let's do it somewhere in the scheduler? Yeah, let's do it. Oh yeah, this code will always succeed right here, this one. In fact, you can follow the process hierarchy in process to any other, okay? Okay. I guess we could just do this. Let's do this. Let's iterate this way, and then let's see what's in the task. Let's print the name. Let's print the name of the task. I think it's the COMM attribute instruct. So let's do this. Forgot where we were at. Was it sketch H where task struct was defined? I think we can go to 11. I think it was 1170 or something like that. No, this is not even the right one. Uh, Kernel include. You know what? I remember it was include Linux sketch.h. Something like this. Was it? Yes. No. What? Why should you just do this? Let's go sketch C. Uh-oh. I don't remember. This is just so hard. I keep forgetting. Ugh. Something here. I'm determined. I need to start learning this code. Okay, so I think it was sketch H. I think it was sketch H. Otherwise, I'll just ask the LM again. Include or Linux sketch H. Okay. So, oh, I'm looking at the wrong thing. That's why. task structs, something like that. There we go. Okay, so we have the com. I'm just gonna call it com. So if we look at com here, this one here. So character array com task com length executable path executable name excluding path. Okay, so we can at least print this thing out here, and maybe the PID too while we're adding. Okay, so step one, where do we put that? Okay, let's do it. Schedule.c, maybe where it actually schedules something. Yeah, let's find a file. Schedule.c. Okay, where is the best place? Where is the best place? Run task? Is there a run? Maybe DQ task. Maybe NQ task and DQ task. Ah, maybe we're onto something here. Let's see. Activate task. Deactivate task. Tasker. There was like in the book, it said there's a file here that would run all this stuff. Where was it? Where was it? Let's see. So set task state? No. Okay, first I want to make a note of this one. Let's kind of copy that as scratch somewhere. Text editor? Okay, yeah, let's make sure we save that. Process creation, working. Maybe we should do. Maybe we should modify do fork, and then when we get back to task struct, yeah, do task struct. Let's do that, and then let's just like print out what gets, what's happening. Yeah, let's do this. Where is dupe task struct? So dupe task struct should be, what was it, fork C or something? Let's see. Let's search for it. Dupe task struct. Come on. Fork.c. Dupe task struct. Right here. Okay, we're getting somewhere. Okay, so I don't really care about the copying part. Let's kind of just iterate through everything. Maybe a bad idea. So here, so let's just do struct task struct task. So we're just looping, and then given some task, we'll print out the com. So here we go. Okay, let's do it in the beginning. Let's make it a very slow dupe task struct. Okay. So technically this should work. So let's declare something called info task. Okay. So task for info. Task for info. And we'll change these guys here to be the same. Task for info. And then task for info. And then task for info. I don't even know if this is gonna work. And then task for info. So we're gonna start out with the current task, and then we're going to just move up. I wonder if this even has a current pointer. We'll see. Okay, let's do print k first. Print k, and I think it was like what was kern info? What was what was that print k thing again? Let's do it. Let's go here. What are some flags we can pass into print k in Linux 2.6 source? So this will go into syslog when we do print k. Kern emerge. Oh, want to be concise. Current. I'm guessing current info. Let's do current info. Current error. Current warning. Current info. Okay, so that's how we do it. Okay, current info. Okay, let's do that. So print k. We would just say average dev like this. Tagged current info. It was like that, right? Average. Okay. So average dev about to print all the tasks up the chain of current. So we do that, and then this is a for loop that will just move up the process tree. So we can just do print k current info, and then we could just do something like, it's formatted, right? So we can just do something like this. Task for info, so that's the current task. We can just say something like com, and then I think we have a PID somewhere, so task for info would also have PID, and I think that's it. We could say name, and then PID is going to be %d here. Okay, let's check to see PID real quick. Oops, where was I? Where were we? Sketch H, yeah, right here, com, and then we should have a PID somewhere. This TED PID right here, PID T PID. Okay, so we do have something. Going back, go up, up, wow. Okay, there we go. Okay. I think that's cool. I think that we're good. Okay, so we save that. We have some code that prints something out. Maybe I should have just went hello world first, but good start. Let's try to see if we can compile and break our kernel most likely. So since we're editing through this through NFS, we can simply go to our console here. Let me see if I can, of our Linux system. Just throw that to 4. Oops. Okay. That is not what I want, but let's see. Okay, cool. Good enough. All right. So since we're mounted on NFS, we can actually technically see this on the other side. So if we were to go to Vim here, so ls c average dev maybe. Okay, yeah. Okay, we did Vim. I think it was kernel include. Wait, what was that? No, it's kernel fork.c. Okay, so kernel fork.c. Yeah. So if I did this and I search for average dev, it should be down here, right there. Okay. I'm on the wrong window. Come on. Okay. There we go. All right. So if we remember how to compile this thing, it's just make J 24. Yeah, so we just make, now that we have that, and then I'm not sure if it should take too long because we have most of it built already. Let's see how our system monitor is doing, our resources here. Ah, we are actually saturating some CPU. Okay. Well, at some points. Seems like it's going well. Yeah, so the idea here is to compile it and then install it and then hope for the best. So I think after this we need to do it was what was it? Let me try to find the flow. Okay, we need to do make J24, right? So to install or to build and install the kernel. Install the kernel. We need to make J24 and then make modules install, I think, and then make install. So these two are actually the sudo, and then we do sudo update grub, and then we should reboot. Okay, let me change the font for this thing. Preferences. Ooh, custom font. What do we have? Mono. Oh, what happened? Mono. Mono Lisa variable regular. Okay, let's do that. Actually, I want it to be a little bit bigger. Okay. What else do we have here? Yeah. Maybe this. That's probably easier on the eyes. Yeah, it's probably easier on the eyes. Let's do it this way. Okay. So that's going to be our guide there. Okay. I don't know how long this is going to take. Let's probably just continue on while we wait, maybe? Probably doing this on the VM was not the best idea. Now that I think about it. Okay. So let's just make that. Okay. So we have finished another chapter, and I'm curious to see how that thing turns out. So I will, let's see what I can do here. Can we kind of just tuck this in maybe on there, and then we can probably do a split, and then maybe kind of just bring it down here and then resize a little bit so we can just kind of monitor what's going on. Maybe this will be okay. And then maybe this side we can do the split this way. Okay. So then, yeah, it's like this. Not bad. Then we'll just like kind of bring it out again later. So we can like, oh, it's time to check. So we can just do this. We can kind of stretch it out. I don't know. We'll see. But I think right now it's good that we can just at least see the progress here. Okay. Process scheduling. Okay. The prior chapter discussed processes, the operating system abstraction of active program code. This chapter discusses the process scheduler, the kernel subsystem that puts those processes to work. Okay. The thing that schedules things. The things that schedules processes, tasks. Okay, the process scheduler decides which process runs when, for how long. the process scheduler, or simply the scheduler to which it is often shortened, divides the finite resource of processor time between the runnable processes in the system. So we have a lot of processes in the system, all of them, like let's say you had 100 processes. Process scheduler is responsible for making sure that the individual processes that you have running get a chance to make some progress to run. Simply because, like, let's just remind ourselves that, like, if we had a single core, single threaded system, and you had 100 processes, you need to eventually kind of take turns, right? In terms of allowing a process to run for like 10 milliseconds here, next process another 10, and process C might take another 10 milliseconds to run. And in between that, it's like context switching, and basically that's what the scheduler does, is like it helps determine like which process to run next and which gets like put back into the queue and so on. So the scheduler is the basis of a multitasking operating system such as Linux. By deciding which process runs next, the scheduler is responsible for best utilizing the system and giving users the impression that multiple processes are executing simultaneously. Okay, so it happens so fast that you think that everything like is happening all at once, but it's just switching so fast back and forth that our human eyes don't even like notice it. So the idea behind the scheduler is simple: to best utilize processor time, assuming there are runnable processes, a process should always be running. Okay, if there are more runnable processors or processes than the processors in the system, some processes will not be given or not be running at a given moment. These processes are waiting to run. Deciding which process runs next, given a set of runnable processes, is a fundamental decision that the scheduler must make. Okay. Multitasking. A multitasking operating system is one that can simultaneously interleave execution of more than one process. So what does that mean? So, well, everything. What does everything we have said mean? Right? Like, okay. So, suppose you have processes. I hate how you know what? That's the reason why I just use this pen. Okay, suppose you have a bunch of processes. Okay. So we'll just call them T1, T2, T3, T4. Okay, so these are the running ones, okay? Running tasks. Okay, so that's what's in your computer. This could be like Chrome. This could be like, I don't know, Photoshop. What else do people with Mac like to use? I'm thinking about Mac people. Maybe VS Code and I don't know, if their iMessage or something like that. Okay, so basically the job of your process scheduler is to kind of determine which task to run next. So basically something like this: T2, T1. Come on. Let's see. Okay, T1, T4, and then T3. Okay, just imagine, like, for example, this takes like maybe 30 seconds to finish, right? To just finish the job. Maybe this is 20 seconds. I don't know. 1 second, then 3 seconds, for example. Okay. So basically, when we schedule things, we kind of schedule little time slices. For example, just like from basic, like, maybe this is 10 milliseconds, 10 milliseconds, 10 milliseconds, 10 milliseconds, right? And this is what your CPU can do. This is what your CPU can actually process. And then once it's done with one round, it can maybe schedule something else like T4 again, right, for another 10 milliseconds. And then maybe it schedules T1 again for another 10 milliseconds. Maybe it schedules T3 for 10 milliseconds. And it just goes on and on and on and on and on until like for example, T3 might finish first because it's estimated that 1 second. Users only use it for 1 second or something like that. And this whole thing is like interleaving, right? It's interleaving. You're taking the small slices and then you're just kind of like combining them together and having like the CPU run individual pieces of it. It's your job for your like scheduler to kind of determine how often and how long to run these tasks or processes in this case. And that's like what it's trying to discuss here. So, and this creates the illusion of multitasking, right? Like really underneath the hood, these things are only running one at a time, right? One task at a time. But since it's moving so fast, you think that it is actually all running at once. So anyway, multitasking. A multitasking operating system is one that can simultaneously interleave execution of more than one process. On single processor machines, this gives the illusion of multiple processes running concurrently. On multiprocessor machines, such functionality enables processes to actually run concurrently in parallel on different processors. On either type of machine, it also enables many processes to block or sleep, not actually executing until work is available. These processes, although in memory, are not runnable. Okay, so processes that are not in this running state, they're either in blocking or sleeping, they don't get consideration in terms of being scheduled to run. So instead, such processes utilize the kernel to wait until some event, such as a keyboard input, network data, or passage of time, and so on, occurs. So they will only go back to this runnable state. So any process that is like blocked or sleeping will turn itself back on into runnable state if some sort of event occurs. Yeah. So consequently, a modern Linux system can have many processes in memory, but say only one in a runnable state. So I'm guessing like a process like in a Linux run queue, the number of them that are runnable is actually much smaller than I had actually assumed. Like because if you do like, let's see, we go here, maybe. Let's open that one. Okay, so we do like PS, for example, maybe UX. Okay. Actually, what's a good way to see if a process is sleeping? Oopsie. Is it? I don't know how to read this. Let's do this. System monitor. Okay. Maybe here. Maybe. Wow. Okay, well, basically, there should be some sort of like statistic that'll show like whether or a state of what the process is, whether it's sleeping or whatever. Active processes. There we go. So maybe only this one is actually awake right now, right? So if we were to maybe, I don't know, kind of split this view back and go here, maybe it'll refresh to something else if I did this. No, let's see. let's make the update interval to be aggressive at 1 second, and then let's also do let's see, what do we want to show? We show priority too. We'll also show status, maybe that's what we want to see. Okay, let's do it. Okay, and then if we were to go here and say all processes, if we were to do this again, priority, status, running, here we go. Okay, so we did running here. We'll find that actually a lot of things aren't actually in the run queue into consideration. Look at that, most things are sleeping. So I don't know how to, let's see, switch process. Can we do running? Yeah, running, run. You see that? Running. Okay, so then we did this. Now we're back to, let's see. Okay, here we go. So if we did this, do we see any updates? Let's see. Do we see any updates? Yeah, we see more updates. See, alacrity comes and goes because it's, yeah, so yeah, not many active processes. Most are actually sleeping, like the book has said. Don't know how else to explain. Okay. Let's see. Okay. So multitasking operating systems come in two flavors: cooperative multitasking and preemptive multitasking. Linux, like all Unix variants and most modern operating systems, implements preemptive multitasking. In preemptive multitasking, the scheduler decides when a process is to cease running and a new process is to begin running. The act of involuntarily suspending a running process is called preemption. Okay, so two differences between cooperative multitasking and preemptive. Cooperative is like the old Windows, like 3.1 days. Maybe old Mac OS too, where when you run a program, you couldn't really use your system aside from running that program, because that program had like total control. There was like no real process scheduling. That program would not have to kind of give back its time to the CPU. It would just continue running until it felt like it would be appropriate to give back like control to the OS. Versus preemption is like where we saw here with this diagram, where each program or task is like forcefully switched away to be more fair. So, and there was like bad things that happened, like with Mac OS and maybe like Windows 3.1 with the cooperative multitasking. Um, some programs would never like yield control back, and then you would just like end up being frozen. So anybody who's used computers like back in the mid 90s, I would say, remember this type of thing where you're using a computer and then all of a sudden your program stops being unresponsive, but at the same time, um, the whole computer was unresponsive, and you would have to sort of uh, uh, turn off the computer forcefully by pressing the power button, and you would actually lose a lot of work that way. So yeah, just the memories. Okay, but with preemption, it's like well, if a if a program ends up uh, not yielding, or it doesn't really matter, because the OS will actually take control back for the next process running anyway. Yeah. Uh, the time a process runs before it's preempted is usually predetermined, and it's called the time slice of the process. The time slice, in effect, gives each runnable process a slice of the processor's time. Managing the time slice enables the scheduler to make global scheduling decisions for the system. It also prevents any one process from monopolizing the processor. On many modern operating systems, the time slice is dynamically calculated as a function of process behavior and configurable system policy. As we shall see, Linux's unique fair schedule does not employ time slices per se to interesting effect. Ooh, so it's not always like 10 milliseconds. It's either calculated or depending on your process scheduler, it could just decide when it's going to preempt a specific process. So, by the way, I'm going to like start removing like stuff from the config. I think one of the reasons why it takes forever to compile is probably because I'm compiling a lot of stuff with it. So, but it looks like it might be almost done. So, anyway. Conversely, in cooperative multitasking, a process does not stop running until it voluntarily decides to do so. The act of a process voluntarily suspending itself is called yielding. So yeah, that's what I meant by the whole like Windows 3.1 and Mac OS thing. You have to explicitly give back processor time to the operating system. So ideally, processes yield often, giving each runnable process a decent chunk of the processor, but the operating system cannot enforce this. The shortcomings of this approach are manifest. The scheduler cannot make global decisions regarding how long processes run. Processes can monopolize the power processor for longer than the user desires, and a hung process that never yields can potentially bring down the entire system. Thankfully, most operating systems designed in the last 2 decades employ preemptive multitasking, with Mac OS 9 and earlier and Windows 3.1 and earlier being the most notable and embarrassing exceptions. Yeah, got that one right. Of course, Unix has supported preemptive multitasking since its inception. Wow, humble brag. Okay, I think this is just about done. So let's move back. How do I? You know, let's just make this full screen. Oops. Oh yeah, it doesn't work that way. Let's bring it back. Or actually, you know what? I could have done it this way. Let's bring it back here, 3, and then let's actually shift it in to here. Oh, how do I do that? Okay. Okay, let's do it this way. Okay, so now we have our notes here. So yeah, we're just about ready here. And I'm going to say this, if this doesn't work, I'm just going to cut the video. It's going too long, so we'll work on it next time. But I just want to like at least make a code change and see what happens. So I'm just a little disappointed it's taking longer than what I would expect. And perhaps we should probably make this a little bit faster by taking out more stuff. Oh no, it's still compiling. Oh wow. I thought it was just ready. It says BZ image is ready. But I think these are all the modules, the drivers. Technically, if it is going through alphabetical order, right? It should, I mean, H for like midway there. My hope. So, you know what? I need to take a break from talking anyway. So I'm just gonna sit here and just like cross my fingers. So yeah, need to come up with a better way to demo all this stuff. And the fact is that I'm recording this in real time too, so it doesn't really help. It's like I think if I were to edit the video, you know, put that effort to edit, it would. This will be the part where I would speed everything up, but no. And it also makes more suspenseful. So okay, anyway, and MNOPQRSTUVWXYZ. Okay, we're still kind of far. All right, we'll continue reading. Let's do this. Shift it back here. Okay. Okay. So Linux's process scheduler. From Linux's first version, 1991, through the 2.4 kernel series, the Linux scheduler was simple. almost pedestrian in design. Makes sense. It was easy to understand but scaled poorly in light of many runnable processes or many processors. In response, during the 2.5 kernel development series, the Linux kernel received a schedule overhaul. A new scheduler, commonly called the O1 scheduler because of its algorithmic behavior, solved the shortcomings of the previous Linux scheduler and introduced powerful new features and performance characteristics. By introducing a constant time algorithm for time slice calculation and per processor run queues, it rectified the design limitations of the earlier scheduler. Cool. The O1 scheduler performed admirably and scaled effortlessly as Linux supported large iron with like servers and stuff. I'm guessing that's what it's trying to say. With tens, if not hundreds, of processors. Over time, however, it became evident that the O1 scheduler had several pathological failures related to scheduling latency-sensitive applications. These applications, called interactive processes, include any application with which the user interacts. Thus, the O1 scheduler was ideal for large server workloads which lacked interactive processes. It performed below par on the desktop systems where interactive applications were the raison d'etre. I think that's how you pronounce that. Okay, beginning early in the 2.6 kernel series, developers introduced new process schedulers aimed at improving the interactive performance of the O1 scheduler. The most notable of these was the Rotating Staircase Deadline Scheduler, RSD, which introduced the concept of fair schedule, borrowed from queuing theory, to Linux's process scheduler. This concept was the inspiration for the O1 scheduler's eventual replacement in kernel version 2.6.23, the Completely Fair Scheduler, or CFS. I don't even know if that's still the same scheduler we use today. Let's see. Linux scheduler. Okay. Documentation. Oh, there's a lot more now. CFS. Let's just see. Is this still the current one? Let's see. The completely fresh server was might not be the current one now. But. Okay, starting from 6.6, it was replaced by the EEVDF scheduler. And I still think it's good to learn. Okay, so moment of truth. Okay, so we're done compiling the kernel. Now it's time to do the sudo make modules install. Come on. That shouldn't take too long. Okay. Next step is to do sudo make install. Okay. Then sudo update grub. Okay. Then reboot, sudo reboot. Hey, there we go. Okay, so since we're outputting to syslog, we should see stuff in the message. Oh, okay, we have a kernel now. Okay, 2.6.34 is what I remembered. It's been a while, Thanksgiving holidays. Oh, you see average dev? Look at all this stuff. Look at that. It's happening really fast, but here we go. Init pid 1, about to print all the tasks. Okay, it might be crashing because. Okay, so this is our kernel change. This is definitely our kernel change. Look at that. Cool. Awesome. Okay, let's log in. So we made our first kernel change, our useless kernel change. Okay, let's take a look at dmessage. That is going to contain all the stuff, the logs. So look at, as we are spawning new tasks, we're just going through all the pretty much all the processes of the chain. For example, this is shell. This one is GNOME terminal, which is what we just spawned right now. So about to print. So we were at bash. So this is bash inside our shell, and that is spawned from GNOME terminal, which was coming from init. Okay. So let's say I did something else and I did mines. I started up mines again. And if I were to do dmessage again, you'll see GNOME mine, right? So about to print all the tasks. So GNOME mine came from init. Okay. So yeah. So Firefox, let's see if Firefox does anything. So Firefox right here, kid 1485 came from init. So yeah. Pretty cool. We made our first kernel change. That's awesome. Yeah, we didn't crash too. I wonder like how intense it is in terms of like how much load did we just put into our system? Like, did we make it even slower because we're printing so much stuff now? I wonder. There's just logs though, so let's see if we were to idle. It's not bad. It feels very passive. Yeah. Anyway, cool. Job well done, all of us, I guess. Our first kernel change here. Talk to you soon.